Okay, so here's this turbulent velocity profile, right? Again, maybe I shouldn't have to reiterate this, but we're going to say turbulent means, right, that. Throwing a lecture, but just so you know, and this is for internal flow only. Don't use this for the external flows, but I'll make that I'll iterate that quite a bit to you. But for this situation of flow inside a straight pipe, the 2000 mark is what we see to be the how to categorize it being turbulent or it being laminar flow. But right, we assumed usually in all these that these are straight, right? It's very smooth surfaces. But let's zoom in on the actual pipe surface, right? And you can already tell, let's say this is a Y, right? That in reality, right, the surface itself could look something like this. This is the bottom of the pipe wall, right? It's not right, obviously. And you can actually get a pretty good measurement of this if you just take on the inside of your pipe one of these little, I think it's a laserometer, where you drag some pin across the surface and you shoot a loop. Someone can correct me on this one. I'm pretty sure you shoot some laser beam at it. And after you drag this across the after you drag this little pin across the surface and you're shooting a laser beam at it right here, the refraction allows you to measure a distance, and then that just goes straight into some computer, right? Takes a signal, and you actually can get this total, right, surface profile plot of your inside of the pipe. So it's not totally abstract the fact that we can get these roughness values, because a roughness value, right, there's some characteristic, right, some statistical measure of this surface roughness. So, right, we define that. There are a couple of them to do. So this is, but a roughness height, we're going to call it epsilon, and it doesn't really matter. But so this is some function of y that your computer spits out, right? One way to do this is you just take like the root mean squared of the function. Right? Root mean squared because we always want a positive roughness height. So I always wondered where those values came from. So I just wanted you to know that these roughness heights are pretty easy to get at. And that's why if you buy a pipe or whatever, some materials just have an inherent roughness value, and there's a table in your book. That's how they're getting them, though. They're just doing it for a lot of the materials, getting that root mean squared of the function value, and then recording it. Okay, spare the detail. But if you do that, same exact process, right? Maybe even something I would assign for this final exam derivation, not confident, but you get this expression for so this is another friction factor, right? Okay. There's another friction factor in there. This is again implicit though, right? Right? It's implicit because F shows up here and then F shows up here. So you can't just use pen and paper and write down what F is, right? It's hard enough to calculate what it is. So I think so people did come around and go, this is just way too hard. So an empirical fitting function is this. 6.9. Reynolds. Right? So this is, let's say this is a nice fitting function from experiments where they fitted this number and they think they fit that number, and you can fit that number as well. The benefit of this, you can see, is there's no F on this side. So for engineering purposes, this one does pretty well because I don't need to do some fancy iteration or use some function solver, even though I think those are pretty easy to use at these points. But if you just have like a calculator, these are helpful because you calculate your Reynolds number, you calculate your roughness height, or you find your roughness height in a table, You get your diameter of the pipe, you calculate this argument, you take log 10, boom, and then you can solve for what the friction factor is. No business of F here and F here. So this one's really good. I like this one. Because with here, I can just write, you can, something like this, you can plug into an Excel cell and just drag down something and it would just spit out all your friction factors. You wouldn't have to tell Excel to do some implicit solve. That being said, if you did some programming like in Python or MATLAB, just go ahead and use this one. Because if you do programming right, you can just have some solve subfunction, easy as pie. For Excel though, this is the easy one. Okay, so next I'll describe this Moody chart, which is a big part of this class, but I think the functions are more important than the chart. No one uses a chart anymore. It's not 1970.